In our previous module, we looked at Docker. Today, we are going to look under the hood at the technology that makes Docker possible, OS-based virtualization. We will explore LXC, the original Linux containers, and understand exactly how the Linux kernel tricks an application into thinking it has its own dedicated computer, without the massive overhead of a virtual machine. By the end of this session, you'll understand that a container isn't a mini VM. It's a highly isolated process. You should be able to explain how containers work internally, understand key Linux kernel features like namespaces and cgroups, and confidently compare containers with virtual machines. You'll break down the architecture into layers, explore the security mechanisms like seccomp and AppArmor, and finally we will actually install and run LXC on a Linux host. OS-based virtualization is a method of creating isolated environments on top of a shared Linux kernel rather than emulating hardware. In a traditional VM, the hypervisor emulates hardware. It pretends to be a CPU and RAM. In OS-based virtualization, we don't pretend to be hardware. We simply use the Linux kernel to create walls between processes. Think of it like an apartment building. Every tenant has their own front door and their own space, but they all share the same underlying foundation and plumbing. This makes containers incredibly fast because they don't have to boot an operating system, they just start a process. OS-based virtualization, also called container-based virtualization, is a technique where the Linux kernel allows multiple isolated environments called containers to run on the same host system while sharing the host's kernel instead of emulating separate hardware like traditional virtual machines. Unlike traditional virtualization, it doesn't virtualize hardware. It uses kernel isolation mechanisms. LXC Linux containers initially released in 2008. The project was developed by engineers from IBM in collaboration with other contributors working to integrate containerization capabilities directly into the mainline Linux kernel. In fact, when Docker first launched in 2013, it was actually built on top of LXC. While Docker eventually shifted its focus toward application-level containerization, LXC remains focused on the system level. An LXC container feels remarkably like a virtual machine. You can SSH into it, run systemd, and manage it like a full server. Yet it remains a container sharing the host's kernel. Unlike traditional virtual machines, LXC provides a lightweight environment that shares the host's kernel. It famously served as the original foundation for Docker before that project developed its own runtime, libcontainer. Today, LXC is maintained as an open source project under the Linux containers umbrella, with significant long-term support and a sponsorship with Canonical Limited. Now, let's focus specifically on LXC, Linux containers. The key idea to grasp here is that LXC provides system containers. While a Docker usually runs a single application, LXC is designed to act like a lightweight virtual machine. It gives you a full init system, like systemd, but without the weight of a separate kernel. How does it achieve this? It uses a suite of core Linux technologies. We have namespaces for privacy, cgroups for resource management, and pivot_root to ensure the container can't see the host's file. For security, it uses seccomp to filter system calls and AppArmor to restrict what the container can touch. To see the power of this, Imagine a hosting provider. In the old days, running 100 isolated Ubuntu servers for 100 different customers would require 100 virtual machines, which would be a nightmare for RAM and CPU usage. With LXC, you can run all 100 environments on a single host. They boot in a second because the kernel is already running, and they use almost zero extra RAM for the OS itself. This makes LXC the perfect tool for multi-tenant hosting and dev test environments where you need a real server feel without the VM performance penalty. A Linux container architecture is built in layers, starting from the physical hardware at the bottom and ending with the applications running at the top. At the base, the physical hardware includes components like the CPU, memory, storage, and network interfaces. These resources are shared by everything running on the machine. Above the hardware sits the Linux kernel, which is the core part of the operating system. The Linux is responsible for managing hardware resources, scheduling processes, handling memory, and controlling networking. In container system, this kernel is especially important because all containers on the same machine share it, instead of each container having its own operating system kernel like a virtual machine would. On top of the kernel is the container engine, such as LXC. This layer is responsible for creating and managing containers by using kernel features like namespaces and control groups, cgroups. At the top of the stack are the applications running inside containers. Each containers can contain one or more applications along with their dependencies, libraries, and configuration files. Even though these applications appear to run in separate isolated systems, they are actually just processes running on the same shared kernel. This design makes containers lightweight, fast to start, and efficient compared to virtual machines, while still providing a strong isolation between applications. Docker and LXC are using the Linux kernel to isolate application without needing a full virtual machine. They achieve this using namespaces, isolation layer, control groups or cgroups for resource control, file system isolation, Linux capabilities, seccomp, system calls filtering, and Mac, AppArmor SE Linux systems. Namespaces are the core mechanism that makes a container think it has its own system resources. Each namespaces create a virtualized view of a resource for processes inside the container. Namespaces isolate system resources so each container appears independent. Types and practical examples. PID namespace isolates process IDs. For example, container can run its own PID1 process, but on the host it might be PID 3456. This means a container can run init or nginx without conflicting with host processes. Net namespace isolates network interfaces. Each container can have its own IP and virtual network interface. Container A can run a web server on port 80, while container B runs another on its own isolated port 80. Empty namespace isolates file system mounts. Container sees its own root / without seeing host directories unless explicitly mounted. For example, you can mount /data from the host into /mnt/data inside the container. IPC namespace isolates shared memory and semaphores. Containers don't share system vIPC or POSIX message queues unless configured. Two containers running SHM won't interfere with each other. UTS namespace isolates hostname and domain name. Each container can set hostname independently. For example, container A web1, container B db1. User namespace maps container user IDs to host. A process running as UID 0 root in the container can map to an unprivileged user on the host, reducing security risks. How does a container believe it's a separate machine? Through namespaces. If I run the ps command inside the container, I only see the container's processes. This is the PID namespace. If I change the hostname in container A, container B remains unchanged. That's the UTS namespace. It's like wearing VR goggle. The process only sees the virtualized world the kernel shows it, even though it's actually running on the same host as everyone else. Control groups. If namespaces are the wall that provide privacy, cgroups are the meter that manage resources. Without cgroups, one container could crash the entire server by consuming 100% of the RAM. Cgroups allow us to be strict. You only get 1 GB of RAM and 10% of the CPU. This allows for high density, meaning we can safely pack hundreds of containers onto a single physical server without them starving each other. File system isolation. Each container has its own root file system, rootfs, which is isolated from the host. Modern containers often use layered file system, overlay fs, for efficiency and image reuse. Key concepts: overlay fs or union fs, multiple layers, base image plus updates, allow containers to share common files without duplicating them. Read-only base plus writable layer. The container can modify files without affecting the original image. This infographic visualizes the concept of file system isolation and layered file system. The central panel illustrates the example of 5 containers, 1 through 5, all sharing a single read-only Python 3.11 base image without duplicating its files on the host disk. Each container is given its own small, unique writable layer for application-specific files, keeping them isolated from each other and the host OS, which is segmented below. Detailed side panels explain the structure. Multiple layers combining to form the visible file system, with modifications contained entirely in the top of layer, ensuring the base remains untouched. Security layers. When we talk about container security, people often worry because all containers share the same Linux kernel. To reduce this risk, Linux provides 3 key security mechanisms. 1. Linux capabilities. Purpose: limit what a process can do even if it runs as root. 2. Seccomp, system call filtering. Purpose: restrict which system calls a container can make to the Linux kernel. 3. AppArmor, Linux. Purpose: enforce mandatory access control policies. Linux capabilities is the first solution. In the old days of Linux, you were either a normal user with no power or root with absolute power. Root could do anything: delete the whole drive, reboot the system, or change the clock. For a container, that is too much power. Capabilities break that root power into 40 tiny pieces. For example, if a container needs to manage a firewall, we give it capnet admin. It can fix the network, but it cannot reboot the host or access other users' file. We give it only the keys it needs and threw the rest away. Cap-net-admin allows modifying network interfaces or firewall rules. Cap-sysadmin broad system administration tasks. Cap-chown change file ownership. Second solution, we have seccomp, secure compute mode. This is a firewall for system calls. Every time an app wants to talk to the hardware, like reading a file or opening a network connection, it sends a system call to the kernel. There are hundreds of these system calls, and some are very dangerous. Seccomp allows us to create a whitelist. If a container tries to make a call that isn't on the list, like trying to modify kernel memory, the kernel immediately kills the process. It's like a security guard at a building who only lets you into the specific rooms listed on your ID badge. Finally, we have AppArmor or Linux. These are mandatory access control systems. While the first two layers protect the kernel, these protect the host file system. Even if a hacker takes over a container and somehow tricks the kernel, AppArmor acts as a final cage. It says, I don't care who you are. This container is only allowed to touch the /app folder. If the hacker tries to look at /etc/shadow on the host to steal passwords, AppArmor slammed the door shut. Together, these layers ensure that a compromised container is like a fire in a room. With a fireproof door, the room might be lost, but the rest of the building, your host server, stay safe. Docker, the application container platform. Now let's pivot and look at the global standard, Docker. The most important concept on this slide is that Docker has a different core philosophy. It doesn't focus on isolating a whole operating system. It focuses on isolating a single application. If you start an LXC container, you expect a full OS to boot up inside it. If you start a Docker container, it starts your Python app, and if that app stops, the container dies. When we look under the hood on the technology list, notice that Docker is using the same primitives as LXC, namespaces and cgroups, but it has added powerful ecosystem tools that LXC didn't. It created the layered file system overlay FS, the build system Dockerfile, and the distributed system Docker Hub. These ecosystem tools, packaging, moving, and sharing immutable images are the secret sauce that made Docker the foundation tools for modern DevOps, CI/CD, and Kubernetes environments. That is the critical mental shift to make. Key focus areas. Why is Docker the industry standard? It comes down to 4 massive business advantages. Microservices. We've moved away from monolith, those giant fragile apps where one tiny bug crashes everything. Docker lets us break apps into independent services. You can update the login container without ever touching the payment container. CI/CD reliability. Before Docker, development was a gamble. Now, the image you test it, the exact same file that runs in production. It's a byte for byte guarantee that eliminates the "it worked on my machine" excuses. Cloud native scaling. Modern cloud, AWS, Azure, and Google are built for containers because Docker starts in seconds. Your infrastructure can auto-scale, launching new containers during a traffic spike and killing them afterward to save money. DevOps source of truth. Docker ends the friction between teams. Instead of passing messy code over a wall, the developer, tester, and ops engineer all use the same portable image. It's a single artifact that works through the entire software lifecycle. This distinction is what makes Docker the perfect engine for microservices. If you are building an e-commerce platform, you don't build one massive application, you break it apart. As seen in our example, the Nginx frontend, the backend API, the Redis cache, and the SQL database each run in their own isolated Docker container. This design gives us incredible agility. We can update the Python code for the backend API without taking down the Nginx frontend. If we get hit with massive traffic, we don't scale the whole server. We just launch 5 more copies of the backend API container. Each service runs independently and can be scaled, updated, or replaced horizontally without touching the other components. Interactive exercise. Service design. Question. Look at our e-commerce example. If we need to run a high-traffic Nginx web server and a low-traffic MySQL database, should we put them in the same Docker container or 2 separate Docker containers? Answer: separate Docker containers. Reasoning: discuss the one container, one process rule. If we put them together, we cannot scale them independently. We would have to launch redundant copies of the MySQL database just to get more Nginx power. Separating them allows us to give MySQL minimal resources while scaling Nginx horizontally to 10 instances. Docker vs LXC. Same foundation, different goals. One of the most common questions in DevOps is, if Docker uses the same Linux features as LXC, why did Docker become the industry standard for apps? To understand this, we have to look at the differences between the kernel and user space. At the kernel level, they are twins. Both use namespaces to create valves, cgroups to set speed limits, seccomp to filter dangerous system calls, Mac and file system primitives. If you look at the foundation of the house, they are identical. However, what they build on top of that foundation is completely different. LXC builds a system container. It's designed to replace a virtual machine. When you start an LXC container, it boots an init system like systemd, starts multiple services, and you treat it like a permanent server. You log in, make changes, and those changes stay there. Docker, on the other hand, created the application container. Docker's genius wasn't the isolation. LXC already had that. Docker's genius was the image system. Docker treats containers as disposable. You don't log into a Docker container to update it. You update the Docker file and build a new image. Think of it this way. LXC is like a pet. You name it, you take care of it, and if it gets sick, you fix it. Docker is like cattle. If an application container starts acting up, you don't fix it, you kill it, and start a fresh one from the immutable image. This disposable nature is what makes Docker perfect for microservices and scaling on the cloud. Docker provides packaging, management, runtime orchestration, networking setup, and lifecycle management. It's a common misconception that Docker is just a wrapper for the kernel. As you can see on the slide, Docker provides a massive amount of user space technology that the Linux kernel doesn't. The kernel doesn't know what a Docker file is. It doesn't know how to push or pull an image from a registry. Docker created the packaging and distribution layers. When you use Docker, you aren't just using isolation. You are using a workflow that allows a developer in Berlin to build an image and a server in Tehran to run that exact same byte for byte copy 5 seconds later. That distribution system, the registry and the image layers is the real secret sauce that separates the Docker ecosystem from low-level tools like LXC. Interactive exercise. Pet vs cattle. Question 1. If you need to run a database where you manually tune the OS parameters every week and keep it running for a year, what you choose, LXC or Docker? Answer: LXC, system container. Question 2. If you need to scale your web server from 1 instance to 100 instances during a Black Friday sale, which would you choose? Answer: Docker, application container. Explanation. Discuss how Docker's immutability makes scaling horizontally much easier than managing 100 individual system containers. That's enough for now. Take care. See you then.